Let's go talk to Mark Wells about rocket engines.
Hey Tim.
Hey Mark, what you holding?
That's a hydrogen peroxide monopropellant motor. It can make up to about 400 pounds of thrust depending on the chamber pressure. And it was designed as it was a prototype for our 56G cancellation motor on the warm gas test vehicle, which is a 600 pound thrust motor.
Cool. Now you guys look like it's gotten pretty hot. You fired that?
It's been fired, and it gets up to about 1230 degrees Fahrenheit.
Uh-huh.
It's running, which is enough to discolor the stainless steel.
Okay. So what can you tell me about this engine? Now, as I understand, you've been designing engines that not only run on peroxide, but you could take this technology and do something different. Because right now, the ISP of this motor is what, sea level wise?
It's about 135 seconds.
135 seconds. Okay, so what can you do with this if you were to add other propellants?
Well, if we were to add kerosene and take this nozzle off, which is bolted onto the catalyst bed here at this flange.
Okay.
That's a catalyst bed from here to about here. And there's a injector up here, which is kind of like a shower head. It spreads the hydrogen peroxide out evenly. And put a kerosene injector in here between the nozzle and the catalyst bed, and we would inject kerosene in radially to burn with the excess oxygen. And at 1240 F, it'll ignite spontaneously, so it's essentially a green
Cool.
hypergolic motor. You know, there's nothing toxic about it. And when it ignites, it's going to make it even hotter by about another 1,000 degrees. So I would not be able to use this nozzle material up to go something like rhenium or a kind of blade material. But what that does is it increases the specific impulse from about 135 up to about 260 at ambient pressure. If I were running as a vacuum engine, about 290 seconds.
So what you're saying is the performance of that engine you're holding in your hand could double.
That's
if
right.
you were to put this extra injection ring for kerosene, go with a little better nozzle materials, and you could double the performance of that engine you're holding.
That's right. For the same mass flow rate, which would be the peroxide plus the kerosene, I'm going to double the performance.
Well, that is really cool. Now, what engines have done this in the past? Is this a new idea, or
No, it's not new. The British were probably the first to do it back in the late 1950s.
Okay.
And then there was Rocketdyne did an engine that was used on the F-104 Starfighter as a booster engine that had a kerosene, or actually it was essentially jet fuel, which is kerosene, JP peroxide motor. So was done commonly in the 50s and 60s, both in R&D and in some limited production applications.
Okay, well, so you're saying this technology has been used in the F-104 Starfighter. Would that be 10 or 20 times, or would that be hundreds of flights?
No, it would be in dozens of flights.
Dozens of flights. So it's not just development. It's pretty mature.
It's pretty mature.
Well, that's pretty cool. So might be a candidate. This is one of the things we're trading right now for propellants. Might be a possible solution for getting us to landing on the moon. If we need high performance, we could possibly use this as an option.
That's right. It's not as high performance as, say, a hydrazine nitrogen tetroxide hypergolic engine, but then again, it doesn't have any toxicity issues. It's safe to handle from a toxicity standpoint.
Okay. So those trades are really being done by Andy Crocker, I believe, and maybe I need to talk to Andy about the trade going on between peroxide and hypergolics. Andy, are you around?
Yes, sir.
All right. Well, why don't you come over here and tell us what's going on, because right now I am looking at a peroxide engine and they've been designing these biprops to take this and make it run on kerosene or RP. And you've, as part of the trade studies for the ILDD, which is the NASA Data Purchase Program, you've been working hard behind the scenes doing trade studies to look at propulsion options. Now, what are we looking at right now?
Well, there are several options. A very simple, straightforward option is to go with a monopropellant hydrazine, which is done on a lot of spacecraft. It's easy to put together, not a lot of components, fairly inexpensive. but the performance of that propellant combination isn't real high.
Okay.
So that means that you've got to carry more propellant, and the volume is larger, and it's a little hard to package in the system. Another we're looking at is another toxic propellant combination, NTO-MMH, or nitrogen tetroxide and monomethyl hydrazine, which is a higher performance, very typical spacecraft propellant combination. Because it's higher performance, it means you don't have to carry as much propellant. The tanks can be smaller, and the overall lander system can be smaller. But again, the propellants are toxic, which brings in a lot of concerns about handling. And it's a bipropellant system, and the components are expensive. So we're looking at those, but we also have the issue, or the possibility of looking at a peroxide kerosene system, which, as Mark has explained, has been done, has some heritage as a spaceflight, long-term spaceflight system, and Earth-based systems. We've got experience handling those propellants, and we feel like that's got some possibilities too. So we're trading all of those.
And this is a pretty short mission we're having to do as we fly to the moon. And right now we're looking at the max stay time on the surface of the moon. I mean, obviously that's not relevant to this. It's more about how long is it going to take us to get to the moon, because once we do that burn and set out on the surface, we're not like some teams that plan to reignite and do a hop. Right now, the lander, the rovers are baseline. So tell me, what are the big drivers for right now for those trades in terms of peroxide, kerosene versus N2O4? What are we looking at? Is it a little more heritage, I guess, with the N2O4 MMH?
Yeah, there are a number of factors. Heritage is a factor. Can we find the components that exist? Can we find vendors who will provide them to us? Or if the vendors don't exist, could we build them ourselves? The cost is a big issue. Obviously we want to close the business case on the whole mission. So can we find the components at the cost that we can afford? Can we get them in a schedule and a time frame that we can afford?
Okay.
But then also, is it going to be something that'll be a good long-term solution? We're not just going to go to the moon one time. We're going to continue to go. So is it something that we want to continue to do, and can do so on a schedule and a cost that we can continue to do over and over again?
Well, how important is, quote, green propellants in this day and time? I mean, obviously there's mission objectives versus green versus reality, and they don't always line up to be as green, environmentally friendly as we'd always like. Sometimes performance drives the solution. So I guess I'm saying is, it sounds like right now we've got to fundamentally have a technical solution that closes. And obviously, what about cost? I mean, if we were to do something in-house based on the technology we've developed versus you going outside and buying these off-the-shelf components, I mean, how does that stack up?
Well, I think we've proven with the test article we're standing next to that in terms of schedule and cost, we can be competitive with anything that's out there, and probably in a lot of cases do a lot better.
Okay.
So if we have to go develop something, we feel comfortable that with enough development and risk reduction that should be doable, we can compete. So we're looking at all those options. There's going to be things that we weigh, but green propellant is important. And how we handle it and being able to deal with it easily, but cost and schedule and all those things factor in. So we've got a lot of trades to finish up, and probably some cool tests to go run to see what works. But I think it's going to be fun.
Well, I agree with you.